In this video, I'm just going to talk something about a linear programming problem. It's an optimization algorithm. There are several algorithms that we can use for process optimization in chemical engineering, but for considering the time limitation, we are just going to focus on maybe only two or three algorithms, or maybe two or three simple methods that can solve something called as a linear programming problem. Shortly, this is something called as LPP. So LPP means linear programming problem. The final exam you can expect up to 20 marks based on this optimization algorithm. I may give you some problem, then I will ask you to optimize a particular function. You know. So what we are going to learn today is something known as, or we can call it as at the moment, geometry of LPP or geometry of linear programming. So we will see some graphical methods, and what I mean by geometry is how this problem will look like on a piece of a graph paper. And then to solve or to learn LPP, you need to know few fundamentals. I'm going to call this as mathematical prerequisites. Mathematical prerequisite means talk something about how a linear expression will look like, how a linear inequality will look like, and so on. Yeah? So with that knowledge, you can solve some really complex problems that rely on LPP optimization algorithm. And the main purpose of this whole video is to obviously to learn something about optimization. I will come back to this topic. What do I mean by this in chemical engineering sense? Shortly, optimization refers to something. If you have a function, either you maximize that function or minimize that function. And since we are dealing with LPP, this function is always a linear function. You know? And then something that we are going to learn is the jargons in LPP. So LPP itself is a jargon, isn't it? Yeah? First time you must be hearing this word LPP. And we will also learn the other terminologies involved in LPP. We are going to deal only with very simple problems, only with two variables. It can be more than two, it can be n number of variables, but for classroom and tutorial problems and obviously exam type problems, it's better to limit ourselves to two variables. If you have more than two variables, okay, still you can solve using some algorithm, for example, like a simplex algorithm, but this is not something that we are not going to cover in this video. But it's also time consuming. You know? So if I ask you to solve an LPP problem using this type of algorithm, you may need up to 40 to 50 minutes. So practically this is not possible to do in the final exam. But if you have a computer, this is something we can do it in less than a fraction of a second. For example, we can use MATLAB, implement this algorithm, and then we can solve an LPP problem. Yeah? And we don't have a PowerPoint for this video, so we are going to just solve some problems. The whole idea is we solve the problem and then we learn the jargons and the LPP and the geometry of the LPP, and we will also try to achieve the main objective, which is to maximize or minimize a function. And then, okay, for as part of LPP, I will give you some MATLAB scripts, which I will post it in the Sarah Learn. So these codes you should try yourself. I'm not going to explain these codes line by line because these are built based on some inbuilt functions available within the MATLAB. So you may need to use the scripts which I'm going to give it to you and solve an example problem. And these example problems I will solve either in this video or maybe during the tutorial hours. So and you can so that you can compare the results that you obtain during the classroom, I mean during the class hours, and then the one that you obtain using MATLAB. So week 10 and sorry, it should be week 9, 10, and 11. So there are whatever that you are going to learn now, there are no coursework elements involved. All you're going to learn is the technique, yeah, and the mathematics behind the LPP and what is an LPP itself, and some of the jargons involved in the LPP problem. So these MATLAB scripts are only for your learning purpose and also to gain some additional knowledge with MATLAB. And this is something you can also add in your CV. You know, so you know to deal with the optimization problems. Earlier, we also how to deal with machine learning. Uh, I mean, to deal with the big data where you may need to implement a machine learning algorithm to get some useful information. Yeah, so that's something we did in the first 4 weeks. And as I said before, there are multiple algorithms that can be used to solve LPPs, but we will stick only to two of the easiest algorithm. This is mainly due to the time limitations, and both of these methods depends on both are a graphical method. Shortly, these are called corner point method or iso. This is not isoplot. This is isocost method or isoprofit method. Isoprofit method. And if we have time, I will explain something about the simplex algorithm, possibly in week 11, or you can, or in week 11, better we will focus our attention to solve an exam type problem. Yeah? You can solve this with your friends in the classroom. So whenever I talk about optimization, there are many ways you can define it, but for this module, for the moment, all we are going to think about optimization is you may have a function that something we will call it as a cost function, and either we have to maximize it or minimize this function. And the process of maximizing or minimizing this function is something we can call it as an optimization. And we will maximize or minimize this function z with respect to several constraints. Yeah? So this z, from chemical engineering point of view, this can be, for example, your productivity. This can be your productivity, or it can be the profit. So we have to maximize either the productivity of the plant or the profit of the plant, subject to some constraints. So, and if this function z, if this is productivity or profit, we have to maximize it. If the function z represents something, let's say maybe utility or the energy requirement, energy requirements, or possibly maybe the raw material that we use to produce or manufacture a particular product. So either we have to minimize it, subject to some constraints. So that's the easiest way to think about optimization. So for the next two weeks, which means I will record another video, which means in both the videos, all we are going to do is we are going to take some function, which is z. This will be typically a linear function. This will be typically a linear function. And we are going to either maximize it or minimize it. So that's enough for the moment. So let's go to the topic of LPP, linear programming problem. I'm going to begin with, as I said, we will see some mathematical prerequisites. So if you should know how to solve a few things. This is something you may know already, but still, okay, just put something here. Yes. Let's leave it to this. So what do you mean by mathematical prerequisites? So I will begin with something called as a linear equation. This is something you already know. So typically, you know the slope and intercept form of a linear equation. Y is equal to mx plus c. For LPP problems, normally we write the linear expression in this form, something like ax plus by is equal to c. This is how we write the linear expression for LPP problems, and this is the typical slope and intercept form. This is something you already know. So what is this? Y is equal to mx plus c. So typically how do we write? So mx minus y equal to minus c. So this is the common way to write the linear equation for an LPP problems. So this is something you have to remember. And two more things that you should remember is something. I think you may know how to do this type of problem. So imagine if I give some two linear equations, and if I ask you to solve this equation, you should know how to solve this. So what do you mean by solve? So x plus y, that's one linear equation, and x minus y equal to 1, that's another linear equation. If I ask you to solve, that what I'm asking you is, say x plus y. So this can be a linear line that may looks like this. Say x plus y equal to 1. And if you try to plot x minus y equal to 1, so this may be x minus y equal to 1. So if I'm asking you to solve means, so I'm asking you to find the point of intersection. So this can be x star, comma, y star. I'm asking you to find this value, x and y, where both these conditions meet. So x plus y will be equal to 1, and x minus y, x plus y equal to 1, and x minus y equal to 1. So how do you solve that? So this is a really simple problem. So just x plus y plus x minus y. I'm just adding these two equations. That's equal to 1 plus 1. So y get cancelled. So 2x equal to 2, which means x is equal to 1. So you plug this value in any one of this expression. Plug in this value in any one of this expression. So what do we mean by that? So 1 minus y equal to 1, or minus y equal to 1 minus 1, or y is equal to 0. So which means these two lines will intersect at the point 1 comma 0, and if you substitute this value 1 comma 0 in equation 1 here, so 1 plus 0, that's equal to 1, that meets this condition. And also you have here 1 minus 0, that's equal to 1, so that meets this condition as well. So you need to find a common point. So that's the meaning of solving these two linear equations. Next thing that you should learn is something called as let me copy paste these ones. Something called as a linear inequality. So what do you mean by that? So this is something similar to linear equations. So linear inequality is almost similar to a linear equation, but it defines a region, typically a half plane instead of a line. So what do I mean by that? So and typically this linear inequality are also called as constraints in LPP. So this is a jargon, constraints. So remember this word. And inequality means it uses some inequality symbols like less than or equal to, greater than or equal to. And one thing that you have to remember is it represents a region, so not a line. So if it's a linear equation, so it will be an equation of a straight line, isn't it, in an xy graph. So if it's a linear inequation, typically it will represent a plane. So rather than a straight line, so it may be a particular plane, and everything above this line, that's one plane, or everything below this line on this two-dimensional graph is another plane. So what do I mean by that? So let's try to solve some linear inequations. So that should help you to understand what do I mean by it defines a region of half plane. These are some equations that you have. So these are linear inequalities. So x plus 2 greater than or equal to 4. So this is something we can write it as x greater than or equal to 4 minus 2 or greater than or equal to 2. So in an xy graph, how this particular linear inequality will look like. So it will, what it says is x greater than or equal to 2. So let's say this is point number 1, point number 2. So everything after this line, that will be x greater than 2, and this line, please follow the pen, so this line will be x equal to 2. So if you look at this graph, so now this whole region, full region become a plane, isn't it? So x greater than or equal to 2 represent this side of the 2D plane. Yeah? Similarly, we can also plot y greater than or equal to, sorry, this should be x plus, or maybe let's say y plus 4 greater than or equal to 10. So how do you write this equation? So this will be y plus 4 greater than or equal to 10, or y greater than or equal to 10 minus 4, or y greater than or equal to 6. So if you plot this linear inequality in a graph paper, so that will typically look like, so let's say x-axis and y-axis, x and y. So if this is point number 6, so everything above this line and this line, which is y is equal to 6, this entire plane represents y greater than or equal to 6. So what we learned so far is if you have a linear inequality, then it represents typically, it usually defines a region or a half plane instead of a simple straight line. So that's the difference between linear equation and something called as a linear inequality. So we are learning the jargons bit by bit. We know what is a linear expression and how to write a linear expression, which is here for LPP problems. And then we know if you have two set of linear equations, how to solve that equation. So we know how to get the point of intersection, which means the point of intersection of the two equation of two straight lines. And now we saw linear inequality. So it typically represents a region, usually half plane in a 2D graph. So you have one dimension, which is x, another dimension y. A linear inequality represent a half plane in such a 2D plane, in such a 2D graph. I can skip it like that instead of using too much of mathematical terminologies. We can just stick to the basics. If you have x and y, which is two-dimensional, isn't it? One x-axis is one dimension, y-axis is one dimension, and linear inequality defines a region instead of a straight line. So this looks like really basic, but you need to know these fundamentals in order to solve some really big problems using LPP algorithms. So now we can take slightly bit more complex equations that has two variables, like the x plus y. So 3x plus y greater than or equal to 4. So let's write this. So 3x plus 4y, let's say this is greater than 4. So maybe we can put the greater than or equal to 4. So if I give you, we have an xy plane where this region corresponds to. So how can you show this equation in a 2D graph? So what I'm going to do is convert this linear inequality into a linear equation. So 3x plus 4y, that's equal to 4. So I changed the inequality symbol into a linear equation. So now we create a table x, y. So this is such a simple thing to do. Put x is equal to 0, y is equal to 0. When x is equal to 0, so y will be 1, isn't it? Yeah. Similarly, when y is equal to 0, so x will be, so 4 multiplied by 0, so x will be equal to 4 by 3. Yeah. So let's calculate this value. What is 4 by 3? it's 1.33. So how we so, so how we represent this linear inequality in the xy graph? So all you need to do is take these values 0 comma 1 and 1.33 comma 0 and just plot it. So let's say this is 1 2 1 2. So x is equal to 0, which is here, and y is equal to 1. So that point is here, 0 comma 1, and another point is 1.33 comma 0, which is somewhere around here. So this point is 1.33 comma 0. So just to connect these 2 points, so this line is nothing but 3x plus y equal to 4. So now we need to find which region corresponds to 3x plus y greater than 4. Yeah? So either on the up this side of this straight line or this side of the straight line. So how do you find that? So pick one point somewhere here. Let's say x is equal to 0, y is equal to 0. So this point is something below the your equation of straight line, isn't it? Yeah? So let's say x is equal to 0, y is equal to 0, which means 0 plus 0. Is this greater than 4? This is false, isn't it? Yeah? So which means the points above this line should correspond to 3x plus 4y greater than equal to 4, and this line, equation of straight line, just follow the pen, this line should be equal to the equation of the straight line given by 3x plus y equal to 4. So this is the plane in the two-dimensional axis. This region represent the linear inequality, which is 3x plus 4y greater than or equal to 4. If it's 3x plus 4y is less than or equal to 4, then automatically that should correspond to this region. So this region should correspond to 3x plus 4y less than or equal to 4. Why is that? Because we see that. So if you pick one point in this region where I shaded with the green color lines, so that is x is equal to 0, y is equal to 0. So if you substitute those values, so 0 plus 0, is this less than 4? Yes, which means true. So which means this region satisfy the condition 3x plus 4y is less than 4. So that's something that you should know before we solve an LPP problem. Now I'm going to give you slightly a bit more two different linear inequalities, or in the language of LPP, these are called as constraints. So let's say I'm asking you to solve the following inequalities graphically. So how do you solve it? So which means you have to find a common region where both of these conditions meet. So which means you have to find the plane in the xy graph where both of these conditions should meet. X plus 4y should be greater than 8, or maybe we can put greater than or equal to 8, and 3x plus 2y should be less than or equal to 6. So how do you do that? Take this linear inequality and convert it into linear equation. X plus 4y equal to 8, and take this linear inequality and convert this into, we can for the moment I'm going to, or maybe for the convenience I'm going to call this as a linear inequation. Yeah? So 3x plus 2y equal to 6. So now make a table x, y. So put x is equal to 0, y is equal to 0. So when x is equal to 0, y is equal to 8 by 4, that's 2. When y is equal to 0, x is equal to 8. Yeah? And similarly for this equation, when x is equal to 0, y should be equal to 3. And when y is equal to 0, x should be equal to 2. Very simple, isn't it? Yeah? So now you have to um, plot these two equations in a piece of graph paper. Let's plot these ones. So let's do something like 2, 4, 6, 8, and similarly 2, 4, 6, 8. Yeah, so first plot these two values 0, comma 2. So that is somewhere around here, 0, comma 2, and then 8, comma 0, which is this point, 8, comma 0. So just to draw this line. So this line corresponds to equation 1. Let's say x plus 4y equal to 8. So x plus 4y equal to 8. And now we can also plot these values. These two values. So 0, x is equal to 0, y is equal to 3. So that should be around here, 0, comma 3. And then x is equal to 2, y is equal to 0. So that should be around here. So 2, comma 0. So draw this, connect these 2 points. So just assume this is passing through this point. So now we have to find the common region. So what we have here, x plus 4y greater than or equal to 8. Yeah? So let's put x is equal to 0, y is equal to 0, and 0 is this greater than 8. So which means, let's see. No, that's not true. So this is false, isn't it? Yeah? So this is false. So this means, so x plus 4y greater than 8 should correspond to this region. This region, yeah. So which means this entire plane corresponds to x plus 4y greater than or equal to 8. And now you take the second equation, which is here. So what it says, 3x plus 2y is less than or equal to 6. So if x is equal to 0 and y is equal to 0, that's 0 less than 6. This is true. So this means everything below this line should correspond to plane represent the linear inequality 3x plus 2y less than or equal to 6. And now we have to find the common region. So the common region is these two. These are the common region where both the conditions meet or both the constraints meet. So which all this shaded region, which just follow the pen, this shaded region corresponds to 3x plus 2y less than equal to 6, and the other equation is x plus 4y greater than or equal to 8. So this is the common region where both of these conditions meet. So these conditions in LPP language are called as jargons. Sorry, my God, sorry. In LPP language, it's called as constraints. Constraints. So far, good. And imagine if I add one more condition. So let's say if I add maybe two more conditions. Let's say x greater than or equal to 0 and y greater than or equal to 0. So x greater than or equal to 0 will look, or maybe just follow the black line now, so which means this is y greater than or equal to 0. and this plane will be x greater than or equal to 0. So in that case, the common region will be, just follow the pen, only this small black region. Yeah. So this black region will also meet the condition x greater than or equal to 0 and y greater than or equal to 0 plus it also meet these two conditions. Sorry, it also meet these two conditions. 3x plus 2y equal to less than or equal to 6, x plus 4y greater than or equal to 8, plus these two other conditions. Yeah? So if I ask you to show a region in the xy graph or a 2D graph paper where all these conditions meet, then you have to convert the linear inequality into linear equation, find the equation of straight line that represent each of those linear equations, and then you have to identify the right region where the conditions meet with respect to the linear inequality. I hope this is okay until this point. So I'm going to solve some few more problems. This will be good for you to practice. Let me do this one, another easy problem. So we are trying to learn this LPP problem by dealing with some really easy expressions. So now find the solution, or we can call it, like, for the moment we can call it like a feasible region for the following system of linear inequalities. So let's start them. So x plus y, so convert this into linear equation. X plus y is equal to 6. Create the table, very simple. X is equal to 0, y is equal to 0. When x is equal to 0, y is equal to 6. When y is equal to 0, x is equal to 6. So, and then so let's plot this one first. Let's say this is 0.6, this is 0.6. So when x is equal to 0 and y is equal to 6, that's this point, 0, 6. X is equal to 6, y is equal to 0, so that's this point, which is this point. So now you connect these 2 points. So this corresponds to the equation of straight line, x plus y equal to 6. So now we need to find the plane that corresponds to this linear inequation. So x plus y less than equal to 6, which side of this line? You know, so it's on the top or in the bottom of this equation of straight line. So let me pick one point below this equation of straight line. Say x is equal to 0, y is equal to 0. So 0 plus 0, is it less than 6? Yes. So which means this side, or this plane, corresponds to x plus y less than equal to 6, and this equation of straight line corresponds to x plus y equal to 6. So altogether this whole plane represents x plus y less than or equal to 6. So now we plot this one, x greater than or equal to 1. So let's say this is x is equal to 1, so which means follow the green line. So this line, so this is x greater than or equal to 1, so this side. Similarly, y greater than or equal to 1, so let's say this is 0.1, so that should correspond to this plane. So the feasible region is where all these conditions meet, or these constraints meet. So x plus y should be less than or equal to 6 within that region. X should be greater than or equal to 1 in that region. Y should be greater than or equal to 1 in that region, and that region will be this one. Yeah? So I'm going to shade those region in gray color. This is the feasible region. So what we did is we find the solution region for the following system of linear inequalities. Before we try to find the solution for a system of linear equations, isn't it? Which is nothing but two straight lines, and then we pick a point of intersection of those two straight lines. So now what we did is find the solution region for the system of linear inequalities. Yeah. So we find the common region, sometimes called as a feasible region, for a system of linear inequalities. So to summarize, the geometric meaning is if each inequality, so each inequality represent a half plane. So that's the meaning of that. So let me copy paste it here so you can read it. So each inequality represents a half plane. So this is what we learned. So I will give you one a system of linear equations. I will ask you to solve this. So how? Let me copy paste. Solve the system. Yeah? So this is a system of linear equation, isn't it? So how do you solve it? So which means you have two equations of straight line. So one can be like this, another can be like this. You have to find the point of intersection. So how do you do that? So x plus y equal to 2, x minus y equal to 4. So just add them. So this will get cancelled. So 2x will be equal to 6, x will be equal to 3. So plug in this value in any one of these equations. So 3 plus y equal to 2, which means y is equal to minus 1. Yeah, something is wrong. This is not correct. So x plus y is equal to, so 2x is, yeah, this is correct. Yeah, y is equal to minus 1. So if you plot it, if you have plot two of these lines, these two equations of straight line will meet at the point where x will be equal to 3 and y will be equal to minus 1. Yeah, so now we will go into slightly a chemical engineering problem. Yeah, so it's a very, very weird problem. So what's the problem is? So we have a batch reactor. So we are producing two products from the same feedstock. Yeah. So what does that mean? I believe you know how the batch reactor works. So we have a batch reactor. So we use the same feedstock to produce a product called A, and then we perform another set of reaction in the same reactor using the same feed, and then we get another product which is called as B. And X represents the kg of A you produce per batch, and then Y represent the kilogram of product B that you produce per batch, and all you need to do is you need to maximize the profit. So maximize the profit. So, and you also have some information. So if you sell 1 kg of so profit from A is 0.3 per kg. So this can be dollar or pound, anything. So if you sell 1 kg of A, you get $0.3. If you sell 1 kg of B, you get a profit of $0.4. Yep. So you need to maximize the profit. So let's define profit is equal to Z. So what we get? So we get $0.3 if you sell 1 kg of X, isn't it? Where X is the kg of product A produced per batch. So let's say 0.3x plus we get $0.4 if you sell per kg of B, and we know that Y represents the kilogram of the product B that we produce per batch. So what we need to do is we have to maximize this function. This function is nothing but is called a cost function. Cost function. So in LPP problem, first we have to obtain this function, which is something called as the cost function. Either we maximize or minimize. So in this case, we need to maximize the profit, so which means we have to minimize this function, which looks like a linear equation, isn't it? 0.3x plus 0.4y, that's equal to z, where z is nothing but your profit. So z is nothing but your profit. So now we need to maximize this linear equation subject to some constraints. At the moment, we don't have any constraints, so which means this is not a really an useful problem in chemical engineering. Yeah? In chemical engineering, this type of problems always come up with some set of constraints. For example, for example, reactor time. Yeah, reactor time, feedstock availability, and then maybe utility requirements, a lot of other things. And then in LPP, one thing that you have to assume by default is x greater than or equal to 0, y greater than or equal to 0. So what this means, so you cannot go to absolute 0 value, so which means you are producing at least some amount of x and some amount of y. So that's the meaning of that. Yeah? So um, x greater than 0 or y greater than 0. X is equal to 0, y is equal to 0. This typically represent the condition when plant shutdown condition. Yeah? Probably we may shut down the plant maybe for cleaning or for maintenance. At that time, x may be equal to 0, y may be equal to 0, and that time your profit may be equal to 0. Yeah, so if you really plot, so what this means is like, so we can choose any value of x. X can be 10, y can be 100. Yeah, so there is no limit. So depending on how many kilograms of A you produced, how many kilograms of B you produce. So there is no limit. You can produce even 1000 kgs per day or 100 kgs per day. Yeah? So there is no condition set for this type of problem. Yeah? So which means your profit can increase. Um, so if you really plot x versus y, your profit can be in anywhere in this region, isn't it? Yeah. So so this entire first quadrant, this extends to infinity. Yeah. So this type of problems, which means there is no optimal solution for this type of problem, as you know, and this means there is no optimal solution, and this type of problem is something we call it as that LP linear program is unbounded. P is unbounded. So which means objective function z can increase without any limit for this type of problems. Yeah. So but this is not a useful problem. This is completely weird problem. So we will add some more constraints that will make this problem looks a bit more realistic and bit more reasonable, yeah, from chemical engineering point of view. So I'm going to add a few more constraints. Let's do that. So this is a very useful problem. What's happening? Okay. You have the same batch reactor producing two products from the same feedstock. So we are producing product A and product B, and X represents the kilogram of product A that we produce per batch, and Y represents the kilogram of product B that we produce per batch. So what we want to do is we want to maximize the profit. So let's say profit from A is 0.3 per kg, profit from B is 0.4 per kg, so which means we have to maximize the profit, which is something we call it as a cost function, Z. This is nothing but profit. So this is defined mathematically by using the expression 0.3x plus 0.4y. So we have to maximize this function subject to constraints. Yeah. What are the constraints? These are really useful constraints, and this really makes sense. Yeah. So what does this mean? So you cannot produce more than 100 kg of per day. So no matter whether you're producing X or Y, the maximum you can produce is 100 kg per day. So that's the limitation, because we don't have a space to store these products. If you're supposed to produce more than 100 kgs, yeah. And there are a few more other conditions, with respect to reactor time. So each kg of product A takes 0.05 hours. Yeah? So to produce 1 kg, it takes 0.05 hours, and to produce 1 kg of product B, it takes 0.1 hour. Okay, and this is something reaction time, you can call it like that. And then we also have some conditions. So since it's a batch process, sometimes we may need to open the reactor, remove the product, and then clean the reactor, and then keep it ready for the next batch. So considering all these times, I mean all the time that we spent on cleaning, and we also make sure that reactor is clean. This is something we call it as validation. So there are set of protocols to make sure that the reactor is clean and is set to manufacture the next product in the next batch. So these are called as a cleaning validation time, and sometimes we may also have some utility limitations. So we may not have a sufficient amount of maybe steam, for example, to heat the reactor to perform this reaction at some particular temperature. So we have some conditions, so which means we cannot operate this reactor more than 8 hours in a day. Yeah. So that's the limit. And then the usual non-negativity, so which means we have to produce at least some amount of X and some amount of Y. So you have to formulate a linear programming problem by defining the decision variables. This is something we are going to learn now. And something called as objective function and all constraints. So what is the decision variables? So this refers to the one that dictates the profit. So which is nothing but the kg of product A and the kg of product B. So these are the decision variables. So X comma Y are the decision variables. And then the objective function is something you have to write. So this is something we already know. So 0.3 times X plus 0.4 times Y. So this is the objective function. And we have to write all the constraints in a mathematical format. Yeah? So this will be something like a linear inequality, which we saw before. And this non-negativity, which I mentioned here, so this itself is a linear inequality, isn't it? Yeah. So X greater than or equal to 0, Y greater than or equal to 0. And you have to write the linear inequality constraint with respect to these conditions. So we cannot produce more than 100 kg, so which means X plus Y cannot exceed, so sorry, this should be less than or equal to 100 kg, 100, yeah. And similarly for here, so you have 0.805 hours to manufacture product A, 0.1 hour to manufacture product B. And we cannot operate, this is per batch, you can consider like that, and then you cannot operate more than 8 hours. So which means, so 0.05 multiplied by X plus 0.1 multiplied by Y. So this should be less than or equal to 8. So this is one linear inequality, this is another linear inequality, and X greater than equal to 0, another inequality, Y greater than or equal to 0. That's another inequality. So you have one profit function, cost function, and then subject to constraints, 1, 2, 3, 4, 4 constraints. So that's, so formulate the LPP means, so this is what we did now. So we know we managed to write the cost function, and then we identify the decision variables, and then we wrote all the constraints. So whatever we did now, that's it's something called as the LPP. Like we write the formula for the LPP problem. Yeah. So too many buzzwords until now, but try to remember it. So now we have to sketch the feasible region on a graph, showing all the constraints clearly. So you may use a simple hand sketch, so just draw it on a piece of paper. You don't need a graph paper to solve this type of problem. And then this is something that we are going to learn right now. So use the corner point method and determine the optimal production quantities of A and B that maximize the profit. What do you mean by that? So you need to find how many kgs of A and B you have to produce in a day, so that your profit will be maximum. Yeah. So subject to all these constraints, all the 4 constraints that I discussed right now, and then interpret the solution. So state how much of each product should be produced and the corresponding maximum daily profit. So you can solve this using something called as not isocorner. This is just a corner point method and isocost method. Okay. So isocost method, this is something we will cover in a separate video. So here I will just show how to solve this type of problem using corner point method. Okay. So let's write the cost function. So z is equal to 0.3x plus 0.4y. Subject to constraints x greater than or equal to 0, y greater than or equal to 0, x plus y less than or equal to 100, and what we have 0.05x plus 0.1y. 0.1y less than or equal to 8. So let's plot all these constraints in a piece of graph paper. It's really easy. So first convert this one into linear equations. X plus y equal to 100. Procedure is simple. X is equal to 0, y will be 100. When y is equal to 0, x will be 100. Okay. And then when x is equal to 0, y is equal to 0, so x plus y will be 0 plus 0, so that will be less than 100. Yeah, this is true. So which means so this should give you some idea about the plane that corresponds to, or not this one, that corresponds to the linear inequation, yeah, like x plus y less than or equal to 100, a linear inequality. That's a right term. So similarly do that for the other constraint with respect to the reactor time. So 0.05x plus 0.1y, that should be equal to 8. So make the table now. So make the table. So x, y. So when x is equal to 0, y is equal to 8 by 0.1, that's equal to 80. When y is equal to 0, x is equal to 8 divided by 0.05. What's that? 8 divided by 0.05, that's equal to 160. Yep. So this is something. Okay, I hope this is correct. So when y is equal to 0, so x should be equal to 8 by 0.05. That should be equal to 160. I think that makes sense. So let's plot these equations. Yeah, all these linear inequalities on an xy graph. So we don't have anything on the negative side. So because we already have the condition x is greater than or equal to 0, y greater than or equal to 0. So x greater than or equal to 0. So that should correspond to, okay, first let's plot these two equations. 0.05 x plus 0.1 y equal to 8. So what's that? 0 comma 80. Let me divide this graph. 20, 40, 60, 80, 100, 120, 140, 160, somewhere around here. Yeah. And then here you have, say, 20, 40, 60, 80, and 100. First plot is 0 comma 80. So that should corresponds to which region? So it should be around this region, isn't it? Yes, 0 comma 80. And then let's say 120, 140, 160. So 160 comma 0, that's this point. So connect these two lines. So this is an equation of straight line that corresponds to 0.05x plus 0.1y, that's equal to 8. And we know that when x is equal to 0, y is equal to 0, so that's something less than 8. So which means, so that linear inequation 0.05x plus 0.1y less than or equal to 8, that should correspond to this plane in this graph. So let's plot the other one which we have here, which is x plus y less than or equal to 100. So which that corresponds to these 2 points. Let's first draw the equation of straight line that corresponds to x plus y equal to 100, and then we identify the plane that corresponds to this linear inequality. So 0, 100, 100, 0. So follow the red mark, red line. So 0, 100 is this point, 0, 100, and then another one is 100, 0. Just connect these 2 points. And we know that when x is equal to 0, y is equal to 0, the total will be equal to 0, that is less than 100. So which means that should correspond to this region, this plane, isn't it? Yeah? So this entire plane should correspond to x plus y less than or equal to 100. So now we have to identify a common region or a feasible region where this condition meet and the other condition 0.05 x plus 0.1 y is less than or equal to 8, and two more conditions, x greater than or equal to 0 and y greater than or equal to 0. So all these conditions meet only in this region, isn't it? Yeah. So follow the green line. So this can be taken as the feasible region. Yeah, so this is the key message. So what we are trying to do is we're trying to deal with some optimization problem, LPP problems. It contains a linear equation, which is your cost function, and then a set of linear inequalities. That's what we are dealing with at the moment. So now we have to maximize the profit. Yeah. So how do you maximize the profit? So where your profit will be maximum. So to identify that, we are going to deploy some method called as corner point method. So in the feasible region, now locate the corner points. So this is one corner point. This is another corner point, which is here. Another corner point is here, and another corner point is here. Follow the screen clearly. Yeah. So which means you have 4 corner points, isn't it? Let's write the corner points. One is this point, 0, 0. Another one is this point, this one. That is nothing but 0, 80, 0, 80. Another point is this one, which is 100, 0. And another one is this point of intersection of this equation of straight lines. So how do you find this point? So if you know two straight lines intersecting each other, and if you know the equation of the straight line, then you can easily identify that point, isn't it? Yeah? So how do you do that? So 0.05x plus 0.1y equal to 8, and then you also have the other equation of straight line, which for the blue line, which is nothing but x plus y, I think. X plus y equal to 100. So this is really easy problem, isn't it? Yeah. So x plus y equal to 100. That's correct. So multiply this equation by 0.1, and then we can solve. So 0.05x plus 0.1y equal to 8, and I'm going to multiply this x plus y equal to 100 with 0.1. So that will be 0.1x plus 0.1y equal to 10. So we put minus sign, sign here. So which means I'm multiplying the whole equation with -1. So which means this get cancelled, and which means you get -2. That's equal to um, 0.05 minus 0.1. So that will be minus 0.05 x. So which means x should be equal to 2 divided by 0.05. So what's that value? So 2 divided by 0.05, that's equal to 40, isn't it? Yeah? So x is equal to 40. So substitute this value in any one of this linear equation. So 40 plus y equal to 100. So which means y is equal to 60. So that means if you go up, so these two equation of straight lines, this blue line and the red line should intersect at the point x is equal to 40, sorry, 40 comma 100. So now you write, now you know the last corner point in the feasible region. So let's put 40 comma 100. So now we have all the 4 corner points. Yeah? So note that if your feasible region has 4 corner points, then you have 4 corner points. If your feasible region looks like a triangle, then you have only 3 corner points. If your feasible region is a polygon, then you may have 5 corner points. Yeah. So depending on the feasible region, the number of corner points will change. Yeah? So that's something you have to remember in the mind. So now write the corner points okay, let's write it right below. So I'm going to write the corner point. So one is 0 comma 0, another one is 0 comma 80, another one is 100 comma 0, and the last one is 40 comma oh, this is not 100, this is 40 comma 60. Last one is 40 comma 60. And now you have the cost function as well, which is z is equal to what? Z is equal to 0.3x plus 0.4y. So 0.3x plus 0.4y. So substitute this x and y in this cost functions, which mean 0.3 multiplied by 0 plus 0.4 multiplied by 0, that's 0. 0.3 multiplied by 0 plus 0.4 multiplied by 80. And here 0.3 multiplied by 100 plus 0. And then 0.3 multiplied by 40 plus 0.4 multiplied by 60. So this is equal to 0. So this should be equal to 4 8 32. This should be equal to 30. And this should be equal to 3 4 7 12 plus 24. So that should be equal to 36, isn't it? Yeah? If the calculations are correct, this is something you can get. Yeah? So z is equal to 36. So which means, so check which one is the maximum here. So 32, 30, 36, and then 0. So this is the highest value. So which means, so this is the point where profit will be maximum subject to all the constraints. Yeah. So what does that mean? So which means you have to produce 12 kg of A and 24 kg of B in order to get in order to make your profit maximum. Yeah. And at the same time, this number also meets all the constraints. Yeah. So which means 12 plus 24, this is less than 100 kg. And then if you go to the other constraint for the reactor time, yeah, so 0.05 multiplied by 12 plus 0.3, I think, I don't remember, 0.1, sorry, 0.1 multiplied by 24, so this will be less than or equal to 8. Yeah? And all this number is obviously greater than or equal to 0, and the 24 kg, that's obviously greater than or equal to 0. Yeah? So, and that's, which means the, if you go back to the problem, if you go to D, state how much of each product should be produced, which means we have to produce 12 kg of A and 24 kg of B, and our maximum daily profit will be equal to $100. So that's all. So what we did now is we tried to implement everything that we learned about linear equation, how to plot the linear equation, and then how to plot a linear inequation, which is typically a plane in a two-dimensional graph paper, 2D axis. And then we also identified the point, solution to system of linear equations. So whatever the basics that we learned, we used to solve a chemical engineering problem. The only thing that we introduced now as part of the optimization problem is the selecting the corner points, and that's why it's called as the corner point method. And once you have the corner point method, you have to find where things are maximum. Yeah, so in this case, it's maximum. Z is equal to 36. Yeah. And from there, we can identify how many kgs of A we should produce, how many kgs of B we should produce, and that completes the problem. Yeah? So that's the whole idea behind the so-called corner point method. So if I can change this problem to minimization problems, I can ask you minimize something, yeah, minimize Z. In that case, the feasible solution will be x is equal to 0, y is equal to 0, because that's the point where your objective function, which is z, is minimum, isn't it? Yeah. So there are a few things that we also learned. That z is called as cost functions, or something called as objective function. Yeah. And then, so this function is defined by the decision variables, which is the kg of A and the kg of B that we produce. In this case, is nothing but x comma y. Yeah. So far good. We can try to solve one more problem, or this is something you can solve it yourself. I will post the solution alone, but you can solve it yourself. Yeah. So how to? So I'll copy paste the problem below here. So I did. It's the same problem. Continue the problem 4. Yeah, which is to produce some kgs of A and some kgs of B, subject to some constraints which we defined already. So now I introduced new constraints. So what are these constraints? Assume we need at least 1.2 kg of feed, you know, so to produce 1 kg of product A. So we need at least 1.2 kg of feed raw material to produce 1 kg of product A, and we need at least 1.5 kg of feed material, because we are sharing the feedstock here. We are producing both A and B from the same feedstock. So you need 1.5 kg to produce 1 kg of B. And there is some limitations to the feedstock availability, which means we have only we can process only 120 kg of your raw material per day, either to produce A or B. Yeah, so this is another condition. And then there is also a daily demand. We need, so there is no room to produce 0 kgs, yeah, which means that you cannot shut down the plant. So you need to produce at least 20 kg of product A per day and at least 10 kg of product B per day. So this is another condition. So which means you have to write 2 more constraints. So I can write those constraints, but it's up to you to solve this problem. Yeah? So with respect to feedstock availability, with respect to feedstock availability, the constraint is 1.2 x plus 1.5 y. This should be less than or equal to 120. And then for the minimum demand, daily demand for both products, which means x should be at least greater than or equal to 20, and y should be greater than or equal to 10. So these are the constraints. Yeah. So if you really solve this problem correctly, you should get some solution that should look like this. Yeah. And then your feasible region will be this one. So this will be your feasible region, and these are the corner points. You already have the answer 2064, 87.5, and then from there you have to identify at which point corresponds to a maximum value for set. Sorry, yeah, that's correct. Yeah, yeah. So you have three corner points in this case, isn't it? Yeah, correct. Yeah. So 2064, 2010, 87.5, and now we need to find the corresponding cost function. I mean the corresponding profit, not the function. Sorry, because cost function is already defined, isn't it? Yeah. So how we defined this? 0.3x plus 0.4y. And now we calculate the z value until where the z is minimum. Yeah. So that should correspond to. So based on that, now your answer will change for D. Yeah. Say if um, so which mean the kg of A and the kg of B that we should produce in order to reach a maximum profit. So this will be dictated by the value that you obtain here. Yeah? So if you think this value is maximum at 20, 64, then we need to produce 20 kg of A and 64 kg of B in order to maximize your profit. Yeah? So that's the whole idea behind this algorithm. Yeah? It's not even an algorithm, it's a graphical method where you execute a series of things in a particular order. So there is another problem that we can solve. So this time I'm going to give you, so I will give you the whole LPP formula now. So all you need to do is solve it. Yes, solve it using the isocorner method which we discussed. So for the moment, let's assume we have a cost function which is already defined. And now we have supposed to minimize this one. So which means this can be maybe the raw material, or this can be utility requirements. So we need to minimize, or this can be, for example, CO2 footprint. Yeah? So it can be anything that we wanted to minimize. So subject to these constraints, minus 2x plus y less than or equal to 4, and we have second constraint, third, fourth and fifth constraint, which is y greater than or equal to 0. The problem is really simple. You have to use the same method that we followed until now. So convert the linear inequality into linear expression. Minus 2x plus y equal to 4. X plus y equal to 3. X minus 2y equal to 2. So make the table x, y. When x is equal to 0, y is equal to 4. When y is equal to 0, x is equal to minus 2. Make the same table. When x is equal to 0, y is equal to 3, y is equal to 0, x is equal to 3. And same for x minus 2y equal to 2, x is equal to 0, y is equal to minus 1. When y is equal to 0, x is equal to 2. So now we can plot these equations. let's say 2, 4, 2, 4, 2, 4, minus 2, minus 4. Let's plot the first equation. So 2x plus y is equal to 4. That corresponds to this 2 points, isn't it? X is equal to 0, so y is equal to 4. So that corresponds to this point. So 0, comma 4. And then minus 2, comma 0. So x is equal to minus 2, comma 0. So that corresponds to this line. So y is equal to 0, x is equal to minus 2, y is equal to 0. Okay, this is correct. And then now we have to find, okay, so when you substitute x is equal to 0, y is equal to 0, so that's 0, that's less than 4, isn't it? Yeah, so which mean follow the red one. So everything below this line should, that plane should correspond to this linear inequality, yeah, this function or linear inequation, we can call it that way. And then x plus y greater than or equal to 3. So draw this corresponding equation of straight line. So x is equal to 0, y is equal to 3. So which is this point. And then x is equal to 3, y is equal to 0. So that's this point. So connect these two lines. So this is x plus y equal to 3. So check the conditions. So when x is equal to 0, y is equal to 0. So that's 0. Is this greater than 3? No, which means is false, isn't it? Yeah. So that's false. So in that case, x plus y greater than equal to 3. So which means, so this linear inequality, this should corresponds to this plane. Everything above this line. Now you can solve this one. X minus 2y is less than or equal to 2. So x is equal to 0, y is equal to minus 1. So that's this point. And then uh, x is equal to 2, y is equal to 0. So x is equal to 2, y is equal to 0. So that is this point. So connect these two lines. This corresponds to x minus 2y equal to 2. So now let's substitute x is equal to 0, y is equal to 0. So that's 0 plus 0, that's equal to 0. And then so what does this mean? So this is true, isn't it? Yeah, which is less than 2. So which means this should correspond to this region because your point 0 comma 0 is here. So where is the common region where all these three conditions meet? So that the common region where all the three conditions that meet is here. Let me put blue color or maybe use a highlighter. That's the common region, isn't it? Yeah. All the all the three constraints meet. Yeah. And now we need to pick the corner points. You have to pick all the corner points in with respect to the feasible region. And if you really manage to calculate, extract all the corner points, so this is something really easy to get. I already showed you how to get the corner points when two lines intersect with each other. So for example, so this is something x plus y equal to 3, and this another equation intersect at this particular point, so that's x minus 2y equal to 2. So how do you find the point of intersection here, for example? So just put minus, plus and minus, so these two get cancelled, so y is equal to 1 and x will be equal to, you can substitute in one of this equation, so x will be equal to 3 minus 1, which will be equal to 2. So these two lines should intersect at the point x is equal to, what did we calculate, 2 comma 1. So that's a point of intersection. So that's how we identify the corner points, isn't it? Yeah. And this corner point, this is something you can get directly from the plot, and then this is something you have to identify from the equation of two straight lines. Yeah. So let me try to show you the answer. So what is the problem here? You should practice, you should know how to use the graph paper. You should know how to identify the point of intersection from two equation of straight lines, and then you should know to identify um, the corner points, and then you should know, first of all, you should know how to formulate the LPP problem. Yeah, so if there is a problem, you have to understand the statements, and then you have to come up with the profit function or the cost function, and then identify the decision variables. Only based on that you can write the cost function, and then you have to identify all the constraints involved. Yeah. The method is really simple. Yeah. So now we know what is a linear equation is, how it looks like on a piece of graph paper. Yeah, it's a straight line, and then we know also a linear inequality. What is that? Yeah. So it represents a plane. Yeah, it's a half plane. So if it's above, that's one plane. If it's below that line, that corresponds to another plane. Yeah. So typically a linear inequation represents or defines a region, yeah, instead of a line. And these the linear inequations are nothing but, it's called as a constraints in LPP. It's a jargon. And then we know how to plot a linear inequation, how to plot a linear equation, obviously. And then we know how to identify the common region, something like here. And then we know how to identify the corner points from the feasible region, and then we pick those corner points, and then we try to calculate something called as the cost function. Yeah, from the cost function, we can identify the condition where your cost function can be maximum or can be minimum. Yeah, so and for this problem, this is something this is something you have to solve. Yeah, this is something I leave it to you, because I added only two more constraints. Maybe three more constraints. Sorry. Yeah. So this is something you can really manage, which means you will get one more linear equation on the xy graph paper, xy plane, and then sorry, xy plane. Yeah, that's correct. And then you need to get another linear line that corresponds to x greater than 20 and y greater than 10. So these are two lines. So this is y greater than 10, and this purple line is x greater than 10, and now your feasible region become completely different. So you identify the corner point. If you know two equations intersect each other, from there you can identify the corner point by solving those two linear equations. And once you have the corner point, you calculate the corresponding z value, and based on the z value, you identify which point corresponds to the maximum z value. So that's the amount of A and B that you should produce in order to maximize your profit Z. Yeah. So for this minimization problem, so, if we solve it correctly, where is that graph? It's not, I cannot copy paste the graph for some reason. I don't know what's the problem. It's not allowing me to show you the results. Oh, anyway, we solved it already here, isn't it? Yeah. So from here you can pick the corner points, identify the corner points within this feasible region, and then from the feasible region, I mean from the corner points, based on the corner points, calculate the z value, and where we and identify the point x comma y where your cost function z is minimum. Yeah. So that's the answer to this problem. So you have to identify the the corresponding value for the decision variables x and y, where your z will be minimum. Yeah, that's all for the moment. And if you want, we can even, this is something you can do it yourself. I'm going to copy paste one more problem here. So I'll just paste one more problem here. Oh my God. Maybe I can show the problem here itself. Uh, So this is another problem that you can try to solve, minimizing the carbon footprint in the product manufacturing using different method. Yeah. So method A is the conventional process. It produces a lot of CO2, but it's a cheaper process. Method B produces emits less CO2, but it's a costlier process. And the question is, the company must produce at least 80 units of the product. Units in the sense it can be any unit, it can be kg or something else. You know? So you have to produce at least 80 units to produce you have to produce at least 80 units to meet the customer demand. And then each method consumes energy and water. Yeah? So these are some constraints that you have. And then we have some other details. Yes, the process of CO2 emission. So this is something related to your cost function. So if you manufacture 1 unit of um, A, you emit 10 kgs of CO2. If you manufacture 1 unit of B, you emit 6 kgs of CO2. And for that, you consume 4 kgs of energy to manufacture 1 unit of A, and to manufacture 1 unit of B, you consume 6 kilowatt per hour. And then you also use 6 liters of water to manufacture 1 unit of A, and you spend 3 liters of water to manufacture 1 unit of product B. And you have some available resources is you cannot spend more than 480 kilowatts per hour of energy, and then you cannot use more than 420 liters of water per day. Yeah, so these are some constraints. So you have to formulate the LPP problem. Oh my God, I don't know what's the problem. Okay, yeah, it's working. So this is something related to your profit, or sorry, cost function in this case. Yeah, so which means you are supposed to minimize CO2 emission, isn't it? Yeah, so which means that this is nothing but CO2 emission per unit kg of CO2 we emit when we manufacture 1 unit of product A and B. So this means 10 times x plus 6 times y. So we are supposed to minimize this function. subject to some constraints. So 4 times x plus 6 times y, and this is something energy requirement, isn't it? Yeah? So we cannot use more than 480 kilowatt per hour. 480, and with respect to another utility which is water, so this is 6x plus 3y. This should be less than or equal to 420 liters, and then we set the usual non-negativity constraint x greater than equal to 0, y greater than or equal to 0. So we are manufacturing at least some product, but this can be eliminated as we have another condition. Oh, no, we cannot, sorry. Yeah. And then what is this? The company must produce at least 80 units of the product to meet customer demands, which means you have one more condition. So we are supposed to produce at least 80 units, either using method A or method B. So in this case, x plus y should be greater than or equal to 80. So which means at least you have to produce 80 units at the minimum. So these are the constraints. So you have how many constraints? 1, 2, 3, 4, and 5. So you have 5 constraints, which means you have 5 linear inequalities, and then you have one cost function which is supposed to minimize. So since we already have formulated the LPP problem, this is something now you can solve using a piece of graph paper. Yeah? So all the procedure is same. Convert the linear inequation into linear equation, and then calculate the correspond, create a table, calculate the x and y, get the straight line, and identify the plane that corresponds to each of these linear inequations, and then identify the feasible region, locate the corner points, and identify the corner point where z will be minimum. So that's the solution for this type of problem. So during the lecture hours, the book projector was not working, so that's why I'm recording this video. So if you know how to solve this type of problems, I think you can. I think this may help you to get at least 20 marks in the final exam. So these problems are not really tough. It's dead easy. Deal here is to write the so-called the LPP formulation, no? To read the problem, understand the problem, and identify what could be the cost function. So in this case, the cost function is something related to CO2 emission, isn't it? Yeah? So how many kgs of CO2 that we emit when we manufacture 1 unit of product A and B, and subject to some constraints that are related to the utility requirements here. So one is the power requirement, energy, and then the another one is the water requirement. This can be maybe used to cool the product or something like that. So subject to all these constraints, and at the end of the day, this is really an easy problem. So if you know how to use the graph paper, how to plot the equation of straight line, how to identify the plane that corresponds to the linear inequation, that's all you need. And then obviously to identify the corner points. So to identify the corner points, you should know if there are two lines intersecting at each other, and if these two lines corresponds to an equation of a straight line, then how to calculate the point of intersection, which is nothing but the solution to two of those linear equations. So we already saw x plus y equal to 1, x minus y equal to 1. You just solve it, and that whatever the x and y value that you get, that should be the point of intersection with respect to these two equations of straight lines. So try to solve this problem by yourself. So it should be enough for this moment. So the next video, what we can do is maybe we can solve, for example, maybe problem 7, for example, the same problem. Instead of a corner point method, we can use the another method which is called isocost method, isocost or isoprofit. Isoprofit method, and then we can even solve another problem. Maybe even this problem we can solve. Problem 6 we can solve using isoprofit method. Even problem 4 is worth to solve using isoprofit method. Yeah. So problem 4, for example. So maybe next video I will show you how to solve this problem 4 using isoprofit method. Yeah, using isoprofit. Yeah, that's all for today.